All right, welcome everybody to the Blazing the AI Trail using LangGraph to conquer the Oregon Trail. Here we have Robert Shelton. He's an applied AI engineer at Redis, where he specializes in vector search and AI applications. Additional introduction to himself, but welcome everybody, and we will be here for an hour and a half. I think you're confusing. Thank you. Go ahead.
Thanks, y'all. Well, like Renee said, I'm Robert. I'm an applied AI engineer at Redis. So what does that mean in practice? In practice, I work with a lot of different companies to kind of help them figure out the question like, we want to do AI, what does that mean? And so a lot of my work is kind of going from, hey, we have this idea, there's all these cool technologies, but how do we actually make this work in a business context? And then from there, I also am a primary contributor to the Redis vector library. So that's a Python package that does vector search and things like that. So a lot of, when you get into this AI world and you're trying to do more, I guess, memory by association, I think is a phrase that we're going to start to hear more, where you want to understand searches that are like things and not just keywords or that sort of thing. What, the AI revolution is really empowering a lot of applications to do is take complex inputs that we would normally not have deterministic maps to and be able to parse that in a probabilistic way. So for this tutorial, the main project repo is here with this QR code. This is, I'll get to it in a little bit. I will have a notebook version available. This is like a full production ready repo that you can just copy and use. It's more of a, when you get to the point where you're trying to take this thing to an actual application you're building for some customer need or something like that, this is more of like a full architecture. There is a notebook version if you just want to get the core concepts and that sort of thing. So the both will be available. And I have, this is the notebook if you want. A lot of my job is pulling data scientists out of notebooks and into the production stack. So I'll give people a second if they want the notebook too. You can also, if you just Google for Redis AI resources, there's a bunch of recipes there. And this is under agents, and this is the full featured agent example. Cool, all right, so let's go back to the beginning. Like I said, this is Blazing the AI Trail using LangGraph to conquer the Oregon Trail. We've already done this. I'm Robert. I'm a PyData engineer. I'm actually from Charlottesville. I grew up here. I don't live here now, but this is taken nearby when I had more of a beard. And I want to start with a little bit of conceptual background of what is an agent. One thing that I am somewhat critical of in the kind of marketing around agents is we refer to AI agents as like a deity, like a third-party entity. Agent is a software architecture. I think that is the better way of thinking about it, because what you're doing is you're putting an LLM in a process loop. That's what an agent is. It's a loop that's going to put an LLM there so it can make decisions on what's the next action to take. This is really powerful, right? Because we've all built applications where maybe there's a rules engine in the middle that decides which API to call next, but now we have this thing that can probabilistically interpret natural language, and that's super powerful. But at its core, it's still a software architecture. I think sometimes we get lost in the sauce of the branding and not focusing on what it is. The other thing is, in practice, when you implement agents, like I said, I work with a lot of different kind of clients on this. You're doing it with graphs, typically a lot of people use LangGraph. That's probably the most popular orchestration framework right now. It's a subshoot of LangChain. I will say probably in the future it'll get phased out and people will do a lot of their own custom stuff as they understand the patterns more, but right now most people are building with LangGraph. So that's what we're going to do today. What's important about LangGraph is we're taking this decision ability with the LLM and we're putting it in the context of a directed flow or a process. And that's what we'll be working on today. So why does this matter? I kind of hinted at this earlier, but LLM's ability to take these really complicated natural language inputs and effectively map to process is amazing. And you kind of get that straight out of the box instead of like, if, I don't know if you've tried to make a rules engine or something where you have all your business logic, you have 1,000 ifs, ands, or else's, and you're trying to route to things and parse different inputs. The ability of LLMs to handle a lot of that in a like out of the box way is what is driving all the hype around agents right now. Will it be used for every problem? No, but is it really effective at some things? Definitely. So our goal today is we're going to build an agent application that illustrates the techniques needed for a real world solution. We're going to understand the structure of LangGraph code outside of a notebook. And we're going to add a pragmatic architectural components to optimize performance and usage. You don't want to just point an LLM at every software problem that ever existed. We've been doing software a long time. There's things we don't need to reinvent the wheel on, and we want to take cheaper solutions with. And then we're going to develop the right tools in our agent to solve the intended problems that we're going to propose. Cool. So what we're going to be building today, this is the architecture. So when one thing that comes up a lot when we're working with people in industry is LLMs are expensive to use, and agents put LLMs in a while loop. So people will implement that and be like, "Oh my God, my bill is this much. I'm gonna get fired." And so we're gonna be building that agent loop. That's kind of the core here, right? So we're gonna have our agent. That's the brain here, and this again. At the center of our process loop is this thing that makes decisions. That's the brain. That's the LLM. Then the LLM is going to have at its disposal tools. So in most frameworks, the agent is going to have different tools. What is a tool? A tool is a piece of code. It's a function you write. In this case, it's going to be a Python function. We're going to write a couple of these. And what does a function do? It takes input, gives an output. And so what the agent does when it invokes a tool is it's like, okay, I'm in this situation where I need to do deterministic math. I'm not good at that. I'm going to call my tool. I'm going to format the input for my tool. I'm going to give that to the input. I'm going to get back my output, and then I can hand that back to a user. So the LLM is often just playing point guard in an agent stack. It's passing the rock, getting the thing, setting up for a shot. I don't know if basketball fans out here, but so in this stack, we're going to be doing a semantic cache, which is basically the idea of if you've already generated an LLM response, why recalculate it? And we're going to use that as a way of kind of reducing. Again, we see this in stacks where you get people overcharging on their LLM bill. We'll have a cache there. We're also going to do a router. A router, I don't know if you guys remember when like the ChatGPT first got rolled out, different companies were implementing it. There was like a Chevy dealership that like just put their model out there, and people were asking like Python questions to the Chevy dealership's LLM because like it was just it's a generally trained model. So a router is a layer ahead of your LLM. That's like I don't want people using my expensive agent workflow to solve problems that doesn't matter to our business. So a router is just basically like, is this on topic or not, and it can kick them out of the loop. Again, if this is a little bit fuzzy, it'll make sense in the code, hopefully. If it doesn't, we can't keep talking about it. So that's going to be our general flow. And then the other thing, I think I heard someone talk about this earlier, we will be using structured outputs in this lab. So oftentimes an LLM will like give you back a paragraph of text, and that's cool, but sometimes what you're doing is you're trying to connect an agent to an API or something. So I actually want a structure, a schema of my output to come out that I can take action on. So we'll be doing in Python. This is often implemented through pydantic models. So we'll be going into that. So cool. If you have found the code, check it out. We're gonna jump in. The other thing just to get used to with LangGraph, it's the architecture, the minimal architecture for an agent is kind of like what we started about. You're gonna have the agent that's the center of your process loop. It can invoke tools. This is a loop, so it can keep choosing to use more tools, and then it'll end. In terms of like a full execution, it would be like this. So I have an agent, uses OpenAI, hits the tools condition, says, okay, I need to use a tool. I'm gonna use the restock tool, go back to the agent, and then it formats the output. So that's That's what an execution of a graph. If you want a visualization like this screenshot is from LangSmith. So like LangSmith is just like an observability tool for LLM applications. So this is kind of like further going it out. But if you are interested in this, this is what we'll be building. You're given an example. It calls the tool. It shows you what it invoked the tool with, and then it'll format the output. And if you remember an Oregon Trail, it's often like choose A, B, C, or D for your output. And this is actually, we're going to use structured output to handle multiple choice questions. So this is kind of the flow of the execution of our agent graph.
So
It also has price estimations.
Yes, it does. Question?
Restock tool is a domain specific. It's an Oregon Trail.
Oregon Trail domain
not a
specific.
language,
Yeah. So it's the Oregon Trail is the business logic we're implementing. So for Oregon Trail consultants today, it's what we're going to be building out. And this is like a lot of code today. Everything is so abstract. This is very easy to do. This would be the code to write this graph. It's pretty simple. So we'll be jumping into that. I'm gonna skip this slide, and then this is kind of a note I like to give people. One thing I see with people a lot is they're used to building software, and software normally is kind of in this deterministic, what I think of as the vending machine. Like I hit A20, I get out Doritos. We're now dealing with probabilistic systems, which these, if you train a neural net, it's going to have an output layer, and the last layer of that is like a softmax function or some sort of PDF that's going to say, what's the highest probability of my next token output? The LLMs at their core are a next word prediction, model. Now, what this can give you is cases where you're not always going to get what you expect. And some people will use LLMs thinking, I'm going to get the same thing every time, like they're in software brain, they're in that thing. We have to start designing systems in mind that we're going to have to accept some error rate. That's the trade-off for the flexibility out of the box is that you're going to have some false positives, you're going to have some false negatives. This is a very data-focused crowd, so I'm sure most people are familiar with the confusion matrix of how you think about output, but more and more as you design software in this age, you're going to have to be thinking probabilistically and not deterministically. And a lot of the times I see engineers or scientists really struggling in this paradigm is they're trying to fit determinism into a probabilistic structure, and it's like maybe you should ask your more fundamental questions. So that's my big thing. So we'll be working through this. If you've looked at the repo, there's a folder called the participant agent folder. There's a full example. It's completed. All this code is public. Everything, if you want it. If you get lost, don't worry. We have a short time frame. This is only an hour and a half. So if you fall behind, that's okay. It's all there for you. But primarily, we're going to be working in the participant agent folder, and we're kind of filling in the blanks there. And we'll try and take questions as we go. We'll see how far we get. There's a good chance we don't get through all the material. It's all in the Readme. It's all there for you if you need it afterwards. Cool. All right, and so it begins. And now I'm going to sit because I sit when I code. All right, so if you're in the repo, oh, actually, last thing I'll call out. Sorry, I said last thing like 7 times. If you're in the repo for the notebook, so if you're in the Redis AI resources, I think I had a friend ask for the notebook. If you come to agents and you go to this full featured agent, that's me if you want to follow me on GitHub. But if this will be the same code, but just in notebook form, if you want to follow along that way. I'll be going through the project repo because I think that's a little bit more novel. But if you just want a notebook, this is all in here, and you should have had a link earlier too. But yeah, cool. Yeah. No, I think it's good to have multiple form factors. Okay, so to the repo. If you go in the repo, you're going to see some prereqs for this. If you don't have them, that's fine. That's just letting you know what I'm set up on. And then is this code, everyone can like read this, it's big enough, hopefully, ish, okay. So what you're gonna do is, have a Python version. You can use different Python versions. I have tested this extensively with like 3.12 just because I happen to be on it. I've been doing it with 3.13 here, so it should work with different versions. You're gonna go through basic kind of setup, set up your virtual environment, activate it. This is all here, and then pip install the requirements. Since we only really have an hour together, I'm gonna go a little bit fast. So apologies, but I want to make sure I get you guys as much content as I can. And then if you've done all the steps, you should be able to do, I've added some testing for you. So you can do like Python test setup, and you'll get setup worked if you've configured your environment right. So don't, if you haven't configured your environment right, don't pass go until you've done that. There's also, all of this is built in. I've built in a testing script. So we're going to be working through, when I initially did this, there's a port, go look for it. There's a 1978 port of the original Oregon Trail that you can run in Python. The problem with that is the LLM just solved it the first time I did it. So I've built out some different test cases to kind of walk through exactly what we're doing, Oregon Trail themed. So that's what we'll be doing. And there's an alias for running the test just so you get a little bit of a prettier version. If you run this code, you'll notice that it's not going to work. It's not going to work at first, right? We're going to fail all of our tests. That's by design because we're going to be, like a good engineer, we're fixing the tests, right? Repeat after me, we fix the tests. So the first kind of scenario we're going to be walking through is just to build our graph. And to kind of illustrate this, the first question on our Oregon Trail journey is just, what is the first name of the wagon leader? If you play Oregon Trail, this is the first thing you're asked. The first name, obviously, of our person is Art, which is short for artificial intelligence. And this is going to be a type of free-form question. So all we want to happen with this is we want to invoke the agent, and we just want it to give us back a name that it like understands. This is just like the hello world of agent examples. So if we come back here, we're gonna start and like engage with what looks complicated. You'll see in this participant agent that I've got a number of kind of files here. And the reason I built it out this way is if you do everything in a notebook, you'll get that like vertical sprawl of like things, and then you'll come back to the beginning, you're like, wait, where did I assign that? And part of what we're, as this space matures is we want to think about things in the same way we build good software, we build good agents, and we want to have good hygiene and practice. This structure I'm using is actually from LangChain itself. So you can like Harrison Chase wrote this structure. This is kind of how they're developing things to help you keep track of the different concepts that you're dealing with in this space. So what we're gonna do, and as we go through, you'll kind of like feel the structure. So the first thing we're gonna do is I'm just gonna take this system prompt. So the first thing a model takes is a system prompt on your LLM, and then I'm gonna go to nodes. So nodes in our file. Let's see if it's opening. So when you get to this file, this is our nodes file. Nodes are the process parts. So we showed the diagram before. Nodes are where things take place. They're the process parts of your graph. Okay, so if a graph routes to a node, it's going to execute something. So this is where we define our executions. The first node in our graph is the agent itself. And what is an agent? It's the LLM, it's the brains at the center of our operation. So in here, you're gonna see this function called getToolModel. It's gonna take in the model name. So for this example, we're using OpenAI. Actually, we have set this up to work with Olama. It's a little flakier because Meta's models aren't as good. There, I said it. So in this function, you're gonna see that you're gonna pick your model. So in this case, we're gonna use OpenAI. We're gonna instantiate an instance with chat, GPT basically. And then you're gonna see this function called bind tools. There's a lot of magic in LangGraph. What this is doing is it's taking the tools from our tools file, and these are the little pieces of code that the agent will then have access to invoking. So under the hood, LangGraph has implemented for you basically a decision logic of agent will give out an output, decide it passes a message. So under the hood, LangGraph is really a state management layer, and it'll maintain state that says, hey, go invoke this tool for me. So this is where you at one point you're gonna like, how does it know to call tools? LangGraph is doing that under the hood for you, and it's binding through this method. So when we get the model, that's what's gonna happen there. In a bit, we'll come back to this with structured output kind of function that'll be used later. Same with some of these other things. Mainly, we're kind of filling in the blanks right now. So I'm gonna update my system prompt. My system prompt is basically just like letting the AI system know what it is. You're an Oregon Trail playing tool calling an AI agent. And then if anybody asks, your name is Art. We're just gonna start at the base level. This is just very, very simple. Then we'll have our call tool model function, and then we'll have a node for our tools. So we're gonna save that off, and remember that we have this call tool model. We'll come back to the Readme. And the next thing we're gonna do is we're gonna open till starting to define our graph. So if we open up the graph, it's our graph file here. Again, most of this has been filled out for you, but what we're gonna do is we're gonna uncomment this to start, and then I'm just gonna get rid of this graph equals none. So this is just kind of like making it easy to look at. So when we start a graph, the kind of boilerplate that just like this is what you'll copy if you ask an AI. If you ask ChatGPT to like structure an AI application, this is what it would spit out. Where we're gonna set up a workflow. It's a state graph. So again, we have a graph that has it as state. So it's just like state is just JSON or like data that's being passed between the nodes in your graph, and that's how it acts on it. So in this sense, we're gonna have, this is just the boilerplate. We have our workflow, and then we add nodes to our workflow. And this is outlined in the README, but what we're gonna do is we're gonna add our first node. And our first node we're gonna call agent. Oh, that's what I wanna do. And it's gonna be call tool model. So that function we defined over here that says, I take in state, I take in the config, I have messages, I have my, this is kind of like how we append to state, and then I have my model and I invoke my model. So my model, just remember, is whatever I configured this to be. In a production application, you'd probably have multiple configurations if you want to switch models. And then we bind our tools to that model. So that's kind of phase one. So we come back, and so we're adding our first node to our graph, which is agent, and it's called call tool model. The next one we're gonna have is tools, and then tool is gonna have, I'm gonna make it plural, tools is going to be the tool node. So when you look at this file structure, here is we're gonna define, the aforementioned restock tool. These are just Python functions. Tools are just Python functions. That simple. It's just Python, takes input, gives output. And then we bind to whatever that is. So if you're, for a tool, there's decorators within LangGraph framework that lets you do this easily, but this would be a multiply tool would look like. Takes A, takes B, A times B, that's a multiply tool. You can do any good Python you can dream up, throw it in a tool, and your agent can use it. Why is multiply a good example? Like we talked about before, LLMs are trained to predict. They're probabilistic in nature. This is deterministic math. I do not want an LLM doing deterministic math. So why is an agent powerful? An agent can kind of know when it's not the right thing to use. So it's going to be like, got a multiply question. I'm too dumb for that. Let's go do some math. So that's kind of what we'll be looking at. So if we come back to our graph, we have two nodes so far. We have the agent, call tool model. So this wrapper is just saying, here's my name of my thing, the label is agent, and then here's the function, here's the process that corresponds to that node. So call tool models, and then tools is the tool node. I set an entry point for my graph. The graph's got to know somewhere to start. Agent, and then you're gonna have here is add conditional edges. So conditional edges is when I make a decision to go to one node versus another. So if you come over here, I don't know why it takes forever to do that. But I'll have a conditional edge, and then within LangGraph itself, again, one of the really frustrating things about this space is how kind of abstract everything is. There's a function I'm just gonna start right here. It's called tools condition. We'll define our own conditional edge function shortly, but just to get a start, this tools condition, if you're interested, is just coming from LangGraph pre-built. This is just a core thing from the package. And then in our routing, we need a way to get back from one place to another. So we add agent to tools. So this is our kind of complete graph here. And I probably messed something up, but we'll run with it. If in this repo as well, there's this little sandbox Python for you. One nice thing is we can check. We did it right. Okay, so this is what we just built. Oh yeah, got a question?
Yeah, I don't have OpenAI API access, so I'm probably not gonna follow along. I was wondering if you could just blow up the text. So
Oh yeah, sorry. Yeah, feel free to stop me at time. I'll just get ranting. But and if you don't have an OpenAI key right now, that's okay. The lesson will still maintain. You can go set it up at some point. Yeah. Is that good for you right there? Okay, cool. So with our graph we just defined, this is what we get out. So we're gonna start. We're gonna go to the agent as to tools. And then it comes back to end. So I can notice here that this is off. So that's the nice thing about visualizing is we have agent tools. What we need is tools back to agent. So this is visualization is important for us dumb humans. That's excuse me. Let me restart the kernel. There we go. That's what we want to see. So this is the most basic. You made an agent. Huzzah. So now, if we did everything right, we can now come back to the terminal. I'm going to run my tests. And you'll see we passed our first question. So if we came back to it, our first question was, what is the first name of the wagon leader? And it's just returning art. Notice here, it doesn't invoke any tools. That's great. I don't need any tools. I just need to answer this free-form question. So the next question that we're going to move to, so that's case one. And the reason I like proposing these cases, if you're working on something in like whatever environment you're working on, whether it be a business environment, academic environment, you're going to be driven by the situations you need to adapt to. And there's different tools. So not every agent workflow is the same. Again, it's an architecture. You're going to pick the tools and the pieces of information that are most needed for your application. So again, we're kind of the team that's solving the Oregon Trail today, but this, use your imagination. There's other ways of doing this. So the next kind of question we're going to try and solve is a little bit more complicated. So it's in order to survive the trail ahead, you'll need to have a restocking strategy for when you need to get more supplies or risk starving. If it takes you an estimated 3 days, so here I'm kind of giving it a word problem essentially. If it takes you an estimated 3 days to restock your food and plan your start with blah, 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 budget, 10 pounds a day to eat and keep a safety stock of 50 pounds. So this is like, when you're taking chemistry in, 9th grade and it's just like, just apply the formula, buddy. Like extract the things, plug it into the formula. That's what we're trying to get the LLM to do here. The other thing to notice is our answer isn't a paragraph. Our answer is just D. We if we were interacting with the CLI of Oregon Trail game, it takes like A, B, C, D. It does not take a paragraph of text. It doesn't, that application doesn't know how to deal with that. There's a lot of applications, if you guys have used API, that are very like, I only accept this, I do not accept that, do not go further. So that's what we're gonna be working on, and you'll see that the type of this is a multi-choice. It's a multi-choice question. Alright, so coming back, again, all the rules are here. We're gonna do a restocking tool. So we already went through the question. So the restock formula if you're familiar with restock formulas, it's this. It's daily usage times lead time plus safety stock. So what we're gonna do is we're gonna go over to our tools and we're gonna start defining this tool. So this is my restock tool. And then what does the restock tool do? I do return daily usage times lead, and then I'm just gonna have all of these as inputs. And this should not scare you because this is a Python function. It's like, there's nothing AI about this. It's a Python function, which is great. I love Python functions. They do exactly what I want them to. And then I'm gonna type this. So I'm gonna say these are all ints. Hopefully, space or whatever. So this description is super important. So you might ask the question, how does LangGraph know to call the right tool? It uses the description. It just says like, it looks at the text you gave it and it's like, this is restocking and this tool looks like restocking. Bob's your uncle, let's use that function. That's how it does it. It's not magic, you know. So I'm gonna cheat a little bit for time's sake because we're moving quick here. I'm gonna go to my example tools. Again, this is all here for you, and I'm just gonna grab this function. I'm just gonna copy it over real quick. So that's our tool. This is the restock formula tool used specifically for counting, like that. The other thing that's important about this one is this. So this is a pydantic model. If you're not familiar with pydantic, get familiar. It's a really helpful serialization. It's like adding typing to Python. It turns out typing's kind of helpful. So what does this do? Our restock input, it has daily usage, lead time, safety stock. This corresponds. This tool decorator is saying when you invoke the restock tool, it needs to apply this schema. So we're just like telling how to interact with this tool. We come back and then we can say restock tool. So this, again, when we see that bind tool models call earlier, it's just gonna add this tool to one of the things that's available to it.
It's an array of
functions
tools to yourself.
Yes, exactly. So we actually don't have to change our graph at all. We can add as many tools as we want. Our graph does not change because the tools node is encompassed within itself. So come back. This is where we're getting in the quick demo time. But so we have that. We have our restock tool. We've updated that. We updated our tool list. The second part of this problem is we expect this as a multiple choice thing. So this is actually super important if you're trying to get your LLM to respond with specific schemas. This is what we want to do. So we're going to jump over to state. So this is the state file, and you'll see that I've already done this multiple choice response for you. We have our agent state. This is what's getting passed around between things, and then I'm adding a new field to this, which is the multi-choice response. So this is a really stupid pydantic model. It's just like, it's a literal A, B, C, or D. It's a field. You can have much more complicated ones. This is more just to illustrate that you can have this. And then if you jump from here, we're gonna go back to our nodes. And what's important here is we now have, we have bind tools. Here we have another function called get response model, and you'll see that this is with structured output. So this is a different model call, and I'm gonna say that model multiple choice response I defined in state is now, I want it to say, okay, hey, when you invoke this model, I want you to use the structured output. So it knows, here's my model, you get invoked, that means I want a response in this model. The the next thing, you know, that we want to do in our graph is that even if we have a model that it's like it knows how to respond, I need to tell it how to route between these different things. So if I come back to my graph, we're gonna make some modifications. So we'll go here. This outlines what we're gonna do. So we did the state part, right? So we updated our messages. We did the nodes part where we updated the structured output to correctly use that. Then we're gonna open the graph file again, and we're gonna add a new node. And our new node is gonna be called structure response. So let's go do that. So we're just adding a new node. So this is gonna be node 3. You see I've done this a few times. And then I'm gonna be modifying my conditional edge here. So for convenience, I've put it here, but we'll walk through what this looks like. So my new conditional edge is gonna go from agent and it's gonna invoke should continue. So should continue is a Python function. Most of the things are Python functions. So it takes state, it grabs the last message of the state, and if the last message is not, you know, structure response, just like can continue through. Now when it comes through here, it's just passing it that string output. You can define more complicated functions like this, but in the LangGraph conditional edge, you know, sauce, it's like agent is where I'm starting, should continues the function, should continue goes in, takes my state messages that pass through the graph, it evaluates, it gets back the word continue, right? If it gets back continue from this function, it's just a string, it goes to tools. That's the next place I want to go. If I get back structure response, I go to structure response. It's not magic, it's saying, hey, I had this situation, I'm spitting out this string, take an action based on this string, just like normal software. And so that's going to be our conditional edge there. And then if we come back to our little sandbox file here, and I'm going to restart this kernel, I restart the kernel so it'll re-import the new graph, and I do this. Okay, so again, this is why you do your little visualizations. I left a piece out. So we went from start to agent. Should I continue? If I should continue, I go to tools. Come back, if not, I go out to structure response. What I forgot in this graph is there's no end. I'm just like, I'm out in purgatory here. I've you know, we're dealing with directed, it's very much like a DAG if you're familiar with DAGs. But we're looping, which is where it's not exactly a DAG. So what I forgot is this part, right? So what I'm going to need is finally I want to add an edge from structure response to end. So I'm going to do that. So we're going to do workflow, add. So I don't want it to agent, I want it to end. And this constant end is just like it's the sync node imported from LangGraph. So there's nothing fancy to that. It's just a thing. We come back, and now if I do it, if the demo gods are with me, should load, and we're gonna get back this sort of thing. So we have continue, tools, structure response, end, right? So that's. Oh no. HTTPS connection read timeout. Oh no, that's not my fault. That's the internet. So the demo gods are not with me. That's okay, I don't need them. All right, we're gonna keep moving. All right, so I think you kind of get the idea there, and then let's test it. Let's see if I pass my own thing. So we'll do our first thing. We passed our first test. Come on, baby. Woo! Passed the second test. There we go. Our little agent that is doing its thing. Like he was so young. He could only tell us his name just a second ago. All right, so boom, that worked. And then for sake of time, we're gonna keep moving. So just to review, what just happened is we asked it this question and it gave us back the answer D directly. Because it went through our structure response, it saw that model that we typed. So if we look at, we go back to our state file here, this multiple choice response can only be a literal A, B, C, or D. This is really big because, you know, if you're trying to write code that can talk to other code, which might be powerful, I don't know if you've thought about that, but that this is something that can be really helpful for that. Cool. All right. Next one, our little agent that could is going. So we have a new thing here where we're saying you've encountered a dense forest near the Blue Mountains, and your party is unsure to how to proceed. There's a fork in the road, and you need to choose a path. Which way will you go? The problem with an LLM is that it knows what it's trained on. It was trained on certain data. If it wasn't trained on the state of the trail today, the state of a trail, I don't know if you guys are hikers, I'm a hiker, but it's like, it might be raining, it might be snowing, which path to take is dependent on that. So one thing that comes up a lot is this is why people introduced RAG. So retrieval augmented generation, the point is like, oh, there's gonna be pieces of information that my LLM doesn't know about because it's time bound, because it's proprietary, because it's whatever, and I need to be able to go fetch those. So that's what RAG is. People think, does RAG work with agents? Agents implement RAG. So, because RAG is just it's like a software pattern. So you can design, if you need context retrieval, if your agent needs to be context aware, you add a retrieval tool. So that's what we're gonna do. We're gonna define a tool that can, you know, get context for us. So let's go to tools. Again, this is where the structure of our application starts to make sense. Once you get really complicated things and you're like, oh, I have 18 tools, which part of the notebook is it in? I don't remember. It's like, no, the tools are in the tool file. The graph is in the graph file. It helps out. Again, for sake of time, and this is like, I'm cheating, but everyone else can cheat here. We're in the AI age. Coding is more copy paste than anything.
It's all about fun.
Yeah, it's the vibe. So if you come over and you go to the example tools, I'm just for time's sake gonna grab a couple things. So I'm gonna grab this. Yeah, I'll just grab all of this. Let's do that. And I'm gonna come back to my normal tools file. And then some of this is like already here, but I'm just gonna drop it in. Alright, so we're gonna have a vector store. So we have a function called getVectorStore. We'll define that in a second. Then we have a create retrieval tool. Because retrieving is such a common pattern of agents, LangChain has a primitive for this. So you can pass it a vector store, and it knows how to add. It like basically decorates that so it knows how to be invoked as a tool. So all this function is doing is it's adding the necessary, you know, input output to like be able to interact with a vector store. What's a vector store? Vector store is a database that's storing a list of numbers, and it does matrix math. That's cosine similarity 9 times out of 10. So okay, cool. So we have vector store as retriever. This thing is going to be called get directions. Again, it really matters what you name things, like because this is how the agents know how to pick the tools, because they're using their understanding of natural language to work their way through the code. And what does this do? It searches for return information related to which routes, paths, trails to take along your journey. And again, we update our tools to have, now we have the retriever tool and the restock tool. Save that. Next, we're gonna go over to our vector store file. So this is what we're gonna be doing here. I'll, again, for sake of time, because we have like 45 minutes, I think. This ends at 5, right? What this is gonna do is we're gonna be using, go figure, I work for Redis, we're gonna be using Redis as a vector store. So this is like kind of a very kind of basic thing. We're gonna have our doc here, I guess. So actually, let me pause for 1 second. What's happening in this file? So from LangChain Redis, we're importing 2 things, Redis config and a Redis vector store. So one part of my job is I write ecosystem integrations with LangChain and LangGraph. So this is just, again, it's just Python code that we've wrapped for you so you don't have to write it yourself. What does this do? It's basically just gonna handle the kind of the primitives that LangChain is used to calling when it calls a vector store, and then under the hood it's gonna go to a Redis database where it's gonna store this fundamental vector. We're gonna be using OpenAI embeddings to create our vectors. Use Hugging Face, use whatever. It doesn't, your vector store is not tied to the model you use. Some people think if I use an OpenAI LLM that I need to use OpenAI embeddings. Not the case. Usually Hugging Face embeddings for vector stores, you can get a lot of the performance with much smaller models. You can fine tune those, like take a BERT model with 768 dimensions, fine tune that for your application. Again, Bob's your uncle, you get a lot of good performance out of that. But in this case, we're gonna use OpenAI embeddings just because that's what I did when I wrote this. And what's happening here, this vector store is just gonna check if your vector store already exists, so it's not gonna keep reseeding data. And then we're gonna do Redis vector store from documents, and we're gonna pass it a doc, an embedding model, and config. This is kind of a dumb example. This is like a demo example of a vector store. Typically, you'd have a lot more objects in this, but what we're storing is the northern trail of the Blue Mountains was destroyed by a flood and is no longer safe to traverse. It is recommended to take the southern trail, although it is longer. So remember, our initial question is like, what trail should we take? LLM has not been trained on the trail information of today. So this would be the equivalent of like if you're about to take a trail, this is like hitting the All Trails API and being like, what's the latest trail data? And then it's gonna hand this data back to the LLM to make that decision. So it's RAG, but the agent can decide when it wants to implement RAG. It doesn't always have to do it. It decides when it wants to. And so that, again, this vector store file is just gonna instantiate a vector store for us. It's gonna come back to tools, that's bound, and then kind of go from there. So if everything goes to plan, we've done this. So this, I had a nice diagram for this, I forgot. But if you're unfamiliar with RAG, this is what RAG looks like. We already talked about that. We talked about embedding models. We created our retrieval tool. Sweet. All right. Let's see. Passed. 1. Boom. Passed. Come on. One more. Boom. 3 passed. 2 failed. We have 5 tests. So what we just did, you can see that. Sorry, this output's a little hard to parse sometimes, but we passed our retrieval tool test. You can look at these tests. They're very simple. They're just like, hey. Oh, actually, that's actually worth. Let's look at that real quick. If you look at the test file for this, and you should write tests for whatever application you're building. If we look at the one we just passed, what's it doing? It takes the scenario as input, instantiates our graph. So we just have an app graph, and then we do graph.invoke. So in your code, if you're working with LangGraph, and let's say you had an API that's like, this is our fancy agent server. Agent server would take an input and invoke the graph like this. And then we're just checking, we're just saying, hey, is the response the answer? Yeah.
Is that scenario schema, is that a Lang specific schema with the type and the multi-choice?
No, that's Robert putting it in JSON. Yeah, that's not specific. Yeah. I've been talking a lot. Do people have some questions real quick if we've been going?
I had one more question.
Yeah.
Which is, you mentioned that for, like, it's gonna expect answers A, B, C, or D and nothing else.
Yeah.
But we're talking about probabilistic system. Is that part still probabilistic, just like 99.999% it'll be one of those, or is that like 100% is gonna be A, B, C, or D?
It's still probabilistic to some degree, but the probabilistic thing that's gonna happen there is it might fail. What's gonna happen is a pydantic model is going to do serialization. So the LLM is gonna give out a response, and that'll have a value in it. If it is not one of those things, it's gonna throw an error. So in that case, I'd rather have an error than have you gave me something that I just can't interact with. Because then in my system, if you think observability of system, it's really helpful to have errors are a good thing. Errors are our friends. Because that's something we can report on and be like, oh, we're seeing that we're having this problem, versus like it hallucinated something to get me through, and now 17 steps down the line, the business process, I don't know, flipped some bit that's like we're all up at 3 a.m. on the pager duty. Yeah, question over here.
Yeah, earlier you had mentioned like, oh, instead of this, this is a very simple use case where you put in like the text information.
Yeah.
It said, oh, it's kind of like calling the Alltrails API.
Yeah.
How much support is there in LangGraph for calling like third-party APIs?
Tons. Yeah, so that there's a lot of you can a common like demo example you'll see is there's a really good DuckDuckGo browser, like but as like a Python thing, so you might like Google for you've like taught your agent how to Google and go ask questions. So there is a lot of support for calling APIs. If it doesn't exist, you've now seen how to write your custom tool, so you can just write a custom tool that knows how to call the API you want it to.
One other thing, if
Yeah.
that API has like extensive authentication stuff, do you know like?
Well, so that would come down to, that would not be an agent issue, that would be, is my service either within DNS or with whatever security things it needs, you could pass a bearer token. So in the same way that you're like, if you've written like a REST API with a backend that can like communicate through OAuth, you would have to do that cookie signing, but that's not a new problem, that's a solved problem. You would just have to write the code in the tool that's able to unpack the correct bearer token or whatever, or be in the right thing, or if you're in like a Kubernetes setup where you have like a DNS layer, like whatever the security, I don't know your security setup, but like that's a problem that we know how to do. You would just have to you'd have to write that glue code for it to work. Yeah, but there's nothing. The APIs don't know it's being invoked by a normal service versus an agent service. It's just that's over the HTTPS. That's not agent specific. Does that answer your question, please? Question? Yeah.
Yeah, I have a question off the deep end. So I've made some infinite recursion bugs in the past. What's the guardrail against an application like this having an infinite recursion leading to an infinite bill?
That's a great call. That is one thing that I really hate about LangGraph is sometimes it'll get stuck in loops. We haven't gotten stuck in loops yet, but I can't promise we won't. In that case, kind of nothing beats if you tried 5 times, don't do it again. Just like stop and this is where we're dealing with probabilistic systems that don't always behave like we want. We might get stuck in a weird loop for whatever reason, and so the guidance on that, this is where it's like you can build, like you can get in this recursive pattern of like you could have an agent cron job that wakes up every 15 minutes and tries all the failed jobs again to see if so you can have these like kind of 2 tower systems, but typically for first thing like you just want to do your data analysis and see how frequently that happens and at what point it is. So if at one, you kind of want to do an exponential back off if you're familiar with that concept from like kind of a normal API. You might call a thing, call it once, if it fails, retry really quickly, then exponentially back off your retries at like time intervals. That you could do an exponential back off kind of thing. That there's a lot of this is not solved, or there's not like, some people just want like, this is the way you do it. And it's like, just like any other software, it's gonna depend on like what you want, but I would maybe try exponential back off for that situation. Yeah.
I just have one thing to add to that. So if you have like a high level agent that's just iterating recursively, like you said, it's just going through a loop. I mean, safety valve is just like put a max number of iterations on that. We have that all over the place. Where it's helpful to have a back off like he's talking about is in your tool calls, because a lot of times the model will do stupid things on its first try, and then you'll be like, oh, I need to update the prompt to fix that. So like passing in a wrong parameter or hallucinating parameters. It's really useful to have like a smallish number of retries for that, so you can kind of debug the system and hopefully you bring that down over time. But you might have things like authentication failures or something. Something happened and you want to be able to surface those things, so like a smallish number of retries. And I think a lot of the frameworks offer like the ability to do retries for specific parts of the graph. So
it's definitely catching up in that way. So yeah. All right, I'm gonna keep moving. So now we've built our agent that can kind of handle our different situations. Oh, one thing I will show real quick. Is let's look. Oh, that's Docker. I want to look at. So if you just to show that I'm not completely full of crap. If you look at our Oregon Trail, actually, that's the next problem, sorry. If we look here, you can see this is what we stored when we created our RAG system. Like we wanted to keep this piece of information that the Northern Trail of the Blue Mountains, yada yada, use that trail. This is stored in this is a hash structure in Redis, but it's stored with an embedding. We store embeddings as byte arrays because it's more space efficient. You can't store that as that, but that's why it looks like gobbledygook. This is when the agent did this last question, it vectorized the input question using that embedding model, did the cosine similarity, and returned this one. Pointless in the sense that I only have one record in this database, right? If you're keeping track, that's kind of stupid. Like this would be, get everything. But if you had a bunch of different things in here, that's how you would fetch. So this is what's happening under the hood. Is it stores it in here.
So you would pre-store all of the facts that you know about the trail.
Right.
Something.
Right. Or so.
But those aren't structured facts. Those are text describing.
Right.
Facts.
And then the other thing is like with this in particular, you can have more complicated structures. Like if you want different in the pattern that's emerging is that embeddings are just a vector. They're just a database type. We're not going to have vector databases and normal databases. You're just going to have databases with vector as a type, so that you can mix and match all these different. A lot of my day-to-day job is like, which metadata fields should we combine with vector search? So that's kind of how that looks. All right. So here we are. We are now okay. So sorry, we just did the retrieval tool. We went through that. That worked great. So now we're talking about semantic caching. So this is the idea that like I've already trained, or I've gotten the same response. So I just want to store that LLM response. Agents are really expensive. They're in a loop, they're doing LLM calls. If I've already generated a good response, and for so many applications, you've already done the work, don't do it again. Store it somewhere. So a semantic cache is just like a normal cache, where it's like, hey, I've already done this calculation, go get me this thing I've already done. Except instead of doing it based on key, like, is it the key or is it not the key, I'm doing it based on a distance threshold and my vector search. So I'm saying
of the user's input.
yes, yeah.
Of
So
the
I'm
question.
So if let's say it's like I'm an e-commerce site and someone's like asks like how do I reset my password versus like reset password. Those are the same question, and I can map those using like vector comparisons can capture that like this is like this, and then map it to the same cache hit. So that's the idea with semantic caching, where you might have a query, goes through an embedding model, you get the query vector cache. If it's a hit, we just respond. We've stored the answer to this. Don't go through the whole thing again, just do it. So we skip my agent workflow. If you come back to the first kind of, this is another one of my soapboxes, but architecture diagrams matter. This is what we're doing here. So we're gonna say, I'm gonna check my cache before, like put dollar signs around this. That's like, before I go to that, I'm gonna check my cache. And that's what we're gonna implement here. It's also helpful because like, sometimes like it's just really fast to hit a cache. So how do we do this? Okay, so here's our question. So I realize this is a hunting example, so apologies to deer fans, but this is how it shows up on the Oregon Trail. There's a deer, you're hungry, you know what you have to do, and I don't know if you guys have played Oregon Trail, you'll get the prompt where it's like you need to hunt, and it's like how fast can you type bang, and if you don't type bang fast enough, you don't eat. So that's the situation we're solving for here, and so. Much like we're actually going to use Redis VL in this situation. So Redis VL is the package that I help maintain, and we've created this primitive called a semantic cache, and it's going to do all that setup for you. It just like makes it easy. So let's start. I'm just going to open up. I'm gonna cheat again and just look at this example semantic cache. So in this case, again, we're just storing one record in our cache right now. You would have more records in your cache, and you might have a process for populating. You might set time to lives on your cache. Depending on your application, you would do that. So what does this look like? So I pull in from the extensions class, I'm just pulling in semantic cache. This is a primitive. This code is all open source, so if you want to go look at how this is implemented, you can go check it out. I'll have links for that. Then I'm gonna have my example. This is the text that I am going to vectorize. Then I have my semantic cache, which is the Oregon Trail cache. I pass it a connection link to the database, and the distance threshold. So again, this is doing cosine similarity. So if the cosine or I guess in Redis we store cosine distance, right? Because I want the thing that's closest. So if this thing is within a 0.1 radius in my vector space, return that. That's my correct value. Yeah. 30 minutes, thank you. We got tons of time. Okay, we can really chat. I like chatting. So and then to store in my semantic cache, I'm just gonna say store my hunting example, and then the response is bang, right? Because we just want it to quickly return that thing. So I'm just gonna copy this real quick, and then I'll go over to my participant. And I'm cheating, but that's what we're gonna have. So,
LLM that's generating the index, how's that configured in this semantic cache?
yeah, so by default we use Hugging Face. If you don't use anything, we use a Hugging Face model. One slight thing, it's not an LLM that creates that embedding, it's just an embedding model. So I mean to make that delineation. LLMs are text models, they respond to inputs. Embedding models take an input and they generate a vector. So they kind of do different things. Really, under the hood of an LLM, the thing that made ChatGPT take off is that first layer. The first layer is actually doing effective embedding. So really, like an embedding model is kind of like a layer of an LLM. They're very like related to each other, but embedding models output a list of vectors or a multi-dimensional thing. All right, cool. And then for this test, we don't have to update anything in our graph because we've suffered enough. So I'm just gonna go run this, and it should proceed. Again, this is a probabilistic system, so I always get like freaked out if it's gonna like decide that. Okay, so we passed 4. So the other part of this test is I made sure that part of the test for if you pass the semantic cache is it has to respond in less than a second. Question, yeah.
Just to demonstrate the semantic nature, could we add or modify this test to say something like, well, it says hungry and starving.
Yeah, so I actually do. So the what I store and what I test on are actually different. One says hungry, one says starving. So
that's what I was asking for, but maybe even
if you
slightly
want
more. Let's see how far away we can get and get.
Yeah.
I guess since there's only one, I guess you'll always get that answer. I guess.
Right. For times, I'll leave you an Easter egg. You'll get a much better example out of this. So in the same repo I shared earlier, we have a whole section on semantic caching using different models and using different things. So I would check if you're interested more in semantic caching. This will walk you through. But I think for time's sake, I think we get the idea that like you can play around with that. Yeah. We also if you guys were at the talk. If you were at the talks yesterday, one thing that my team is working on is we actually trained a model specifically for semantic caching. So my coworkers Tyler and Sajith were presenting on that if you caught it yesterday. But that basically there's different gotchas with caching when you're not just doing, we're not just doing is key there, is it not? We found that a lot of people can serve a lot of things from cache if you have a very regulated process. There's also research that is very interesting. We were working with a PhD student at Virginia Tech, where I went, and he actually found that like we tend to repeat ourselves with LLMs like 30% of the time. So there's a large caching volume where we're having these GPUs spin all the time when we don't need to. So, but yeah, we can talk more about that if we get through all of the material real quick. Alright, so we've done the semantic cache, so the next thing and the final thing, our final kind of test here, if we look back, I'll just look back at our questions real quick. So we did our dense forest, we did our deer question, and then now I'm gonna have a question which is tell me about the S&P 500. And it's like, that ain't what we're about right now, this is Oregon Trail and Oregon Trail only. And so the answer is you shall not pass, and then that type is kind of an action. So what we're gonna do here is a kind of a similar idea. Routing, let me pull up my diagrams on this. So we're implementing an allow block list router. This is actually a very similar concept to semantic caching, but we've added code to make this more extendable for different situations you might. So in this case, the query is going to come in, we're going to embed that model, right? One of the big things about vector databases is like you get a classification algorithm for free. People used to train vector models just to say like, is this close to this? If you have that in a database now, you can like really quickly do a bunch of reads. It's basically a classification model, or it's what we would have called a classification model 5 years ago. But anyways, now I'm riffing. We're going to take our router references. So these are pieces of things that we do not want our agent to interact with. We'll have examples of that. We're going to hit the semantic router, and then we're going to have basically, is it Oregon Trail stuff? Okay, go. Agent workflow. If it's not, if it's boring finance stuff, eject. So what we're going to do here is this is pretty like, again, this is kind of for speed of tutorial, this is like it's simplified. But if we come over to the router, this is what we're gonna do. So it's kind of similar, again, like we've already made this class for you so you don't have to like think about it. But our references is like things about aliens, corporate questions about Agile, anything about the S&P 500. Like those are our blocked route. So you could do this in the positive case too, like I could give a billion examples of Oregon Trail things and be like matched to the good case. You can also do this with, this is just showing one route, you can do as many routes as you want. So often in situations we'll have customers who are like, in this case I want to use this database, in this case I want to use this database. It's a router kind of question. You can have as many of these as you want. So again, I'm just going to copy this for now, but what's going to happen is when you do this, the references, this is what we're going to check the inputs that come in against. Then the router is going to vectorize that. So this is using Hugging Face. So this is just an open source model. Then we'll have, this has an overwrite function, but this is going to handle all of it for you. And then when we do the test itself, if I look at test participant for this last one, what it's going to do is you just invoke the router. So this is our router, you give it the scenario and a distance threshold, and it'll come back as one of those. So, and I'm just checking that it got blocked. That's what my test is. So if I jump to router real quick, and we walked through this code, I think you get the idea. We should now be able to test it. And at this point I've gotten to 80%, so I think I pass, even if they were talking earlier about grades, and I was like, I never needed to get 100, just 92, baby. Alright, cool. So we can see it's like, tell me about the S&P 500. We got that. You shall not pass because we matched on our router, we hit the block list, and we went through. So, congratulations. Our little agent that has solved our like Oregon Trail scenarios. That is the content I have. I want to show you guys the congratulations screen. Just like, this is the best part of the Oregon Trail, is you get the mountain scene. But yeah, that's all I have for now. But I wanted to have some more time for questions if people have them and stuff. Yeah.
Yeah, Rob, just quickly about the Redis vector DB offering.
Yeah.
Could you maybe expand a little bit of that on that? specifically, I know that Redis is mostly in mem.
Yeah.
Are you leveraging Redis search? I was just kind
Yep.
of surfing for code. Okay.
Yeah.
Okay.
I feel like my boss planted you here. That's do you hear
So-
that, Kyle?
Sorry.
No, you're good. No, I think that's great. So, in terms of the offering itself, so Redis, a lot of people know Redis as like a caching solution. That's like historically what it is. It is an in-memory database. We do have more offerings in terms of like storing data on disk as well. Where we fit into a lot of our work now and kind of the reason for the Redis vector library, which is what I work on, is we have a lot of these AI search use cases where we need really low latency. So we're just like the fastest vector database. That's the upshot. All of this search works through Redis. So like again, if you look at this database here, actually, this is a good example. So the bouncer is what we made with the router. You'll see that this has a route name, a vector, and a reference. Redis search, you can do vector search with like pre-filtering. You can do any of the metadata fields. You can like linear combinations of BM25. So that our search offering works into a lot of flows. The other thing, people with agent workflows, there's a really good example that one of my colleagues recently finished, but we do a lot with short-term and long-term memory for agents, because one problem we don't. So again, this comes to the architecture thing. I've kind of been the narrative we've been building here is you want to pull the right things into your agent workflow that you need. In a lot of applications, the LM needs to keep track of what we've been talking about, and that's the memory layer. So there's short-term and long-term memory. So OpenAI, when you chat with ChatGPT, it actually uses Redis for the memory layer. So it's storing your conversational history there so it can fetch it back. And then that's like, there's a problem with LLMs we call the tell me more problem, where it's like if I've had a chat and I'm like, we're chatting about hiking trails, and I'm just like, and then, I'm like, oh, tell me about the AT and like where I get off on this thing, boom. And then I ask questions like, actually flip the route. You're able to do that. I don't have to retype all the thing I said before. It knows because that's in memory. You have to store that somewhere. So often if you're doing like quick interactions, we'll store that in like a Redis DB layer. Yeah.
That makes sense. Yeah, you kind of answered, I guess, from where I was coming from initially.
Okay.
How do you basically configure a system where you have that more available information and something that's like in a colder storage?
Yeah.
In a way. So because I didn't think about vector DBs in that way before, so that was interesting.
Cool. Question in the back.
There used to be Redis graph, but now it's like Falcon DB. Do you know how this can be used in a similar way to do like a graph rag?
So I couldn't hear you.
Yeah, there was there used to be a product called Redis graph, but it spawned off to be Falcor DB.
Oh yeah.
And so I was wondering if there was anything you could do here similar to graph rag, because they keep talking up about how.
Yeah, to be completely honest with you, that's before my Redis tenure, so I don't know. I don't want to hallucinate as much as I hallucinate a lot, but I need a context for I don't know the answer to that. Yeah. Other questions? Yeah.
Please correct me if I'm wrong. So in this case, the cache is basically fetch the answer in the database if the question is similar enough.
Yeah.
What we have asked the agent to answer before. But if there's any changes in the, for example, in the tools, in the workflow, in the agent, or in the RAG, in the knowledge base it is referring to, how we would know, do we rebuild the whole cache or refresh some of them? How do we do the project?
Yeah, I mean, that question is what the question I'm on calls talking to people about all the time, because it really depends. So for instance, I'll give you a couple scenarios. If you're like an e-commerce site that has very similar questions about like the same, or like let's say like insurance, you have the same questions over and over again, you might only update your cache once a week. And the thing you can do is like, This is again why I try and move people away from just notebooks into like production code. What you would probably do with that is typically you would write like a cron job in Kubernetes, like I am the cache cron job, and my job is every day at like 12 p.m. or something, I wake up and I check the cache, and then I could have a simple policy which is just like 24 hours, evict the whole cache, and we'll lazy load the rest of it. Or it can be like you can write a process like looked at my database, looked at my thing, do I need to recalculate? Yes or no. So the truth is there's no silver bullet to that question, because what people are caching really depends on the process. Like you might have frequently asked questions that like never change, and like you don't need to change that very often. Or you might be caching stuff because you're like, we have some apps that are doing like thousands of queries per second. So those, you could have something that lives in the cache for 7 minutes, but it still saved you, 3,000 recalculations. So those sort of questions, I'm not trying to like dodge your question. It's just like it really does depend. That's the engineering we're still doing. So you still have to do engineering with agents, like it still happens. Yeah.
Could you do like dependencies of certain cache entries?
Yeah.
Like the insurance, you could say, oh well, last night we got new insurance rates for Virginia. So I need to destroy all of the cache that's related to Virginia questions, but not necessarily anyone else.
No,
Is that possible?
Oh yes, totally.
Or
So
because you've already done the vectorizing, how do you know that it has?
well, so this is the nice thing about being a database is like I could add a field on. So this is how the cache record is stored. It has embedding, but I could store some metadata that's like if you could link it in that way if you wanted to. That would be I might steal that idea. Thanks for that. I'll sign whatever you need me to sign on that idea. Question. Yeah.
Did you have some use case for Llama Index as opposed to LangGraph?
Yeah. So if you're interested in how to do this in Llama Index, I don't have an agent example for that. But if you want, this is how to do RAG with Llama Index. So a lot of these things you can swap in and out. Llama Index's agent framework I've used less. We do see a lot with LangGraph. That seems to be the most popular right now. But yeah, all these same concepts, that's something I've actually worked on. We have a Redis integration with Llama Index. So like the same like with vector store, you could do with Llama Index. Yeah. Is that how hopefully? Yeah.
Have you played around with Crew AI at all?
Tyler has.
Does he swear a lot when he uses it? Or does he swear less than you when you're using LangGraph?
We probably swear the same. We're kind of getting I guess Tyler's one of my coworkers that he knows, so we were talking about. But we kind of feel with I guess this is kind of just a comment about like which frameworks to use.
Yeah.
The frameworks really help you get going really fast. Sometimes this is like if I had a critique of LangChain and LangGraph, which they're great. They're very optimized for your first happy path, like set up the thing, because they're trying to drive traffic where it's like someone wants to download it, get an agent working, and be like, yay, I'm a genius. But when you get into like the nitty gritty, sometimes then you can want to like bang your head against several bricks. Sometimes just writing some of that yourself becomes better, but I can't really speak to Crew AI. I haven't used it a ton. Yeah. You back.
Follow up on that one. Did you guys use AutoGen instead of Crew AI? That's another framework.
I haven't.
By Microsoft.
Yeah, I wish I had infinite time. Like people are like, "Have you tried?" They're like, "You're an AI engineer. You should have tried this." I'm like, There's like a million things to try a day, but yeah, I haven't tried it, so maybe it's good. I don't know.
My previous boss did, and he liked it a lot. But we've moved away. To your point, we've moved away from frameworks to like building our own stuff from scratch where we need to.
Yeah, build it yourself. Love that DIY. All right. Question.
You mentioned when you were talking about the router that you could build a router to go any number of paths, and when you introduce more moving pieces and you have this probabilistic thing to deal with on it, how would you think about or approach testing? That's sort of a two-part question. Like how would you approach testing, and then how much do you think that a system that you build like that might be self-correcting and not like run up your credit card bill, for, you know, that sort of thing? Like,
Yeah.
I don't know if those are related enough.
Yeah, let me see if I understand. I want to address it right. So it's kind of like, it seems kind of like a trade-off question a little bit of like, one, how do you test these systems for like probabilistic outputs with like a router versus an LLM? And then is the thing self-correcting? When you mean like the agent self-correcting in terms of like it doesn't go through extensive loops, or?
A point that somebody had made earlier this morning on testing LLM output was that like at some point you're going to hit a good enough point, or like a point where of diminishing returns on your testing whatever, and so you know maybe there's like one extra loop than it should have had of going back, but maybe that's not, you know, awful or something
Yeah,
like that.
yeah, like what's the cost trade-off there? So my general recommendation on that front is, I don't think that this question kind of comes up a lot of like how you should evaluate an LLM application. I think it should be your test suite that you run should be tied. You should have statistics on like whatever you're trying to do. So like precision recall, that kind of stuff. There was a good talk from some of the S&P 500 folks yesterday on kind of like the basics of that. I would say it's not a problem that we should be attempting to solve in a generalized way. It's a problem that you should look at your process and be like, you should solve it. I think you should optimize through your SLAs. So it's like, we need to serve this amount by this like metric, like time. Like go to the traditional software metrics. If I'm getting responses out at this rate and that's good, then if I'm incurring a little extra loop cost, that's kind of fine. But you should hopefully this, I think I'm answering your question earlier. Like, I don't think that's a generalized problem. I don't think it's like, oh, like all LLM processes should be judged like this. It's like, no, you should tie it to like the same SLAs you'd have for whatever REST API you were writing, 5 years ago. You should have for your service, which is like, what's the rate limit on how much I can spend on this? What's like this? And then if you're under those, I would write them at a top level. Let the agent do what it's gonna do, and it just needs to conform to those. If you don't need to like add a router layer because it's like it's operating, the agent is doing it well enough, then don't. But like I would do very high level, the kind of top level things if that helps. Yeah. Oh, 8 minutes. Okay. Any more questions? Yeah.
Earlier, you just defined something up that's or schema.
Yeah.
Do you have any guidance, like or thoughts about how you could go about approaching thinking about that?
For like adding structured output to LLMs, like in schemas. Yeah, I mean, I think that example was kind of show the case where it's like, and it's a common thing that comes up where it's like, I'll see people and they're like, I just want the agent to respond in like one of these two formats, and like the prompt just gets like longer and longer and longer, and you're like doing that game where you're like nudging it one way and back. The structured output I think is really impactful because you're trying. Discrete software is better than probabilistic software, so the more you can get it into like, I know exactly what I need. I know exactly what I want and need. The more specific you can be with like what I want from my LLM, the better, because then you're reducing that like error space essentially. So in to like, just for those who might be curious of what he's kind of talking about, is in our graph we had this structure response node, which is like how we determine to respond. The nice thing about, I didn't point this out where we're going, this is optional. So the agent can actually choose not to respond in multiple choice format. It can just respond free form too. It can decide whether to invoke the structure it needs. It still passes the first use case. If you remember, the first use case is a free form response. It's not multiple choice. But in terms of like how this got defined in our node, you'll see that we bound. So we had bind tools. That's how the LLM has access to the tools. Then we had with structured output. So this is where we pass that one. General guidance: try and like, really it's gonna be like, your API needs these 7 fields, extract those 7 fields for me. Sometimes you might have cases where like, let's say you have really large context responses or something, you might wanna be like, here's my free form, like my large response, and then also give me certain metadata things, because then I can check deterministically on that afterwards if I need to like go different places. So you kinda wanna preserve, it's kinda like if you're writing in, like if you're writing an API and you're like, what should I include in the response? Like I used, like when I was writing APIs, I used to be like, as little as possible. And then over time I was like, yeah, just give them everything and like they can do what they want. Sometimes you do want like a little bit of like, oh, I've given some fields that can help you understand the response too. Where this shows up in practice is when we're doing generation steps, we can actually give like, what was this based on, what was like, you can ask your LLM for more. So it's like, give me a response and in JSON structure, give me this, and this. And that can be really helpful for one, telling your users what the heck happened, or two, like just having more logical flows afterwards. Yeah. Any other questions? 3 minutes to go. I mean, you guys are amazing for like staying engaged till 5 p.m. I would be falling asleep. I'm awake because I am talking. But yeah, I guess I don't think I'm forgetting anything. If you are interested, all this code is online. You could just like use it, download it. You should have all those things. Yeah, so thank you. Thanks for